Hey. I don't even pretend to know your names. I have no idea. Like Jim, Mary, Candy. I have no idea of that. The PSAT for this lecture is going to be assigned after the quiz because we finish up the stress transformation this week. So we do not assign a PSAT on Friday because you have the quiz that week. Okay. So all the stuff that we do this week, you just have to store it someplace in your mind and in your notebooks, and then it's coming as a PSAT later on, but it will come. And it's pretty nasty stuff this week. I think that Lorna timed their trip to England in a very precise manner so as to avoid this whole week of equations. Because it's so random. So I'm like, what do I need to do? And she said, stress transformations. I'm like, right. So it's going to be a little equation intensive this week, but there's not much I can do about it. And she got to do the movie on the guinea fowl running and the bones and all the cool stuff. And here I am, X, Y, X prime, Y prime, for a whole week. Is this a better eraser? Oh, this is a nice eraser. Ugly chalk. So should we get started? We ready? Should we get going? Okay, so this is going to be 3 lectures that start today and go the whole week. And I'm going to stop today wherever we get in this hour, but it's a continued kind of concept over the whole week. So, and this continues from what Lorna started on Friday. So at the beginning of each lecture, I'm going to have boards ready on when we were last time. So the stuff that's ready is not new stuff, it's what we did last lecture. But for me to start from zero every lecture is going to be impossible because I will need things that we did the lecture before that. So I'm going to have the boards ready with what we did last time. And then whenever we end the hour, we end, and we continue the next lecture with this whole presentation. So this whole week is a kind of a week dedicated to understand better the whole stress concepts and understand more how you quantify the state of stress at one point in a loaded body. So last time we started with essentially going back to the very basic concepts of if you have a body with loads on it, then you can go at a point in the body. So this is point P in the body. And then if you have defined a reference frame, an XY reference frame, what you can go is you can go there with your little cookie cutter, zip, zip, aligned with the axis, with the xy axis, right? So you go there and you go exactly at the point in which you are interested, and with your little cookie cutter, zip, 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 you cut an element of the material, and then you take the element out, and on the faces of this element, which is aligned with the Cartesian axis, you have exposed what is the stress inside the material at that point. We okay, right, with that? So the stress at that point, you need to express it in terms of the normal stresses on the faces orthogonal to the Cartesian axis and the shear stress. And we know that we can organize the components of the stress in a little matrix form. Remember, this is symmetric. And these are the components of stress that you see if you cut an element of material at P with faces aligned with the xy axis. Pretty much, right? Everything is good. And I want to remind you that all what we're going to derive today and Wednesday is going to be in the very special case of plane stress. So we're only going to see problems and stress states in which there is no sigma zz or sigma zz, like Lorna would say. So there is no sigma zz, there is no sigma zx, there is no sigma zy, xz, yz, no z. Okay, so everything lives in the xy plane. So the only components of stress are these guys here. So this is the definition of stress as you know it, based on the Cartesian component x and y. And then on Friday we asked the question, but what if we are interested in what faces at a different orientation see? What if we are not interested at those faces there, but we are maybe interested at faces which are at an angle, like that? Maybe we have a crack in that direction. We want to see if the crack opens. There may be different reasons. Maybe we have fibers along that direction. We want to see how is the stress on the fiber and so on. So what we do is we cut around P with different orientation. So we take our cookie cutter, boom, and we cut around P. But now we cut at an angle. So the direction in which we cut now is not anymore the original x and y, but is at x1, y1, which are rotated by an angle theta. Remember, theta is positive counterclockwise with respect to the original xy axis. So now we have this x1, y1. We align the cookie cutter with that. We isolate an element aligned with this axis. And we ask ourselves, OK, so what are the normal and shear stresses on these faces? So we call them sigma x1, sigma y1, tau x1, y1. And in order to find them, the trick is simply to take a wedge of material, cut a wedge, and put it in equilibrium in x, in y, and moments in z. And by putting this wedge in equilibrium, you find the relationship that tells you what are the stresses, normal and shear, on these faces, which are at an angle theta from the original faces. So you can find this equation simply from equilibrium, and you obtain these guys here in terms of the original guys, sigma x, sigma y, and tau xy, and the angle theta. Okay? So this is what kind of we did last time. And we left by saying, if you really want, you can actually look at the derivation of these equations in your readers. So you can see how applying equilibrium you obtain this equation. And there is a little bit also trigonometry to go from theta to 2 theta and simplify a few equations. But the bottom line is that if I know what is the stress state at point P in one coordinate system, in an xy coordinate system, I can find what is the x and y prime of 1 components of the stress in any other coordinate frame, so any other x1, y1 frame, which is rotated by an angle theta with respect to the original frame. And in order to do that, I just plug and turn the crank. Okay? So let's do a simple example before we go a little further in that. So let's see how we use this in a practical way. And it's very, it's water everywhere. No problem. We got, it's the flood. Okay. All right, so let's say that I come to you and I give you, as I was saying, so let's do an example. Example of how you use these equations. So I come to you and I tell you that at point P in the body, and by the way, I always say point P because the stress in general in a loaded body is not the same everywhere, right? So for instance, if I have a bar and I put a force here, then I put another force, you have done problems like that in which you saw that the stress is a certain amount in one part of the bar and then is different in a different part of the bar. So the stress is something which is defined at each point of the body. So at each point of the body, I'm going to have a certain state of stress. And I come to you and I tell you at a certain point P of a loaded body, I know that the stress on an xy element, so in an element like the one on top, an element aligned with x and y, I know what the state of stress is the following. I know, bless you, I know sigma x, this happens to be minus 46 MPAs. I have sigma y, which happens to be 12 MPAs, and positive, actually I have, yes, and I have tau xy, which is equal to minus 19 MPAs. Okay, so I'm given this. This is stuff I know. Somebody went there and measured the stress along those axes. And what I want the stress on an element which is at 15 degrees clockwise from xy. Okay? So I know what is the stress in the original configuration. I have an element which I obtain by rotating 15 degrees clockwise from the original orientation. And I want to know what is the stress in the new element, in the element at 15 degrees. And I want to sketch the stress state, just to see what it looks like. Sketch the stress state. So you want always to sketch the stress state on an element to start with these problems. That's always your first step. So your first step is to look at what you're given and make a picture of it. You always start with a picture. So you're told that if you go in xy, and by the way, I'm not going to continue to repeat that this is a special case of plane stress. That's why I always give you only x, y, and xy, right? Because in all these problems that we're going to do today and on Wednesday, there is going to be no sigma z, xz, and so on. I'm not going to repeat it again. But essentially, everything is going to be only these three components. So I'm given these three components. So the first thing that you do is you draw your little element. Actually, draw it a little lower. So you draw your little element along the axis. And on this element here, so this is an element around point P. On this element here, you look at your stresses. And you see which way they're going and how big they are. And you draw them on the element. And remember that positive stresses go out. So the normal stresses go out. And the shear stresses on the xy face, on the x face goes with y, and on the y face goes with x, right? So these are the positive components of stress. So if I look at this thing, I see that sigma x is minus 46 MPa. So this is my x face. So that means that on the x face, I'm going to have compressive 46 MPa because this is negative, right? So I have, from this, I can see that sigma x is negative, so it's compressive 46 MPa. I see sigma y is positive 12 MPa, so I have 12 MPa like that. and I see that tau xy is negative 19 MPa. So negative means it goes opposite to the plus convention. So it's going to look like that. And remember, I always draw also the ones on the opposite phase that must be there to provide equilibrium both in translation and rotation. So this one here, oops, see, I already screwed up. There you go. So this thing here is shear stress of magnitude 19 MPa, and I take into account the fact that I have a minus sign by drawing it in the direction opposite to the plus convention. Here I don't write minus 19 MPa, right? Because this is the magnitude of the shear stress, 19. And the fact that it's negative is, you see, because it goes in the opposite direction. The same way here, I do not write minus 46 MPa. Okay? Are we good? Brilliant. Okay, so now what do? Is I look at these expressions here and I see stuff that I need. I'm going to need sigma x plus sigma y over 2. I'm going to need sigma x minus sigma y over 2. I'm going to need cosine and sine of 2 theta. No problem. So I say prepare stuff, sigma x plus sigma y over 2. If you do your calculation, it's minus 46 plus 12 divided by 2 gives you 17 MPAs. Then you do sigma x minus sigma y over 2, and that gives you minus 29 MPAs. Actually, that's minus 17, minus 29, because it's minus 46 minus 12 divided by 2, 29. And then the angle theta, I'm told, is 15 degrees clockwise. So the new axis, I'm going to look like that. This is going to be my x prime, and this is going to be my y prime. Actually, x1, y1, if we want to stay with the same convention. Okay, because they are 15 degrees going down like that. So this is 15 degrees. And so the angle theta is what? Plus or minus 15 degrees? Minus. Excellent. So theta is equal to minus 15 degrees, which means that 2 theta is equal to minus 30 degrees. So if I look at what I need, I'm going to need cosine of 2 theta, which is cosine of minus 30 degrees, which is going to be equal to square root of 3 over 2, and this 0.866. And I'm going to need sine of 2 theta. So that's sine of minus 30. So that's going to be equal to minus 1/2, minus 0.5. So you do all this preparatory work. Just turn the crank, substitute the numbers you have, and of course you have tau xy equal to minus 19. So my original stress state on the body here, I kind of like it when you write it in a matrix form. So you're told that sigma x is minus 46, tau xy is minus 19. So on the other side, you also have minus 19. And sigma y is 12. So this thing in MPa is the stress state on an element at x. So up to now, we just rewrote what we have been told and done some calculations of basic stuff we're going to need. And now we just turn the crank, right? Just turn the crank, substitute stuff in there. So when you substitute things, you find that sigma x1 is equal to plus minus 17, which is the average of x and y, plus minus 29, which is x minus y, that multiplies the cosine, 0.866. Then you have plus the shear stress, which is minus 19, that multiplies the sine, which is minus 0.5. So you see, just substitute into that equation on top, average x minus y and tau xy, the sine and the cosine, and then you do the simple algebra, and you get minus 32.6 MPAs. Then you turn the crank on the sigma y1, and you get same thing as before, plus minus 17. And then the y, the equations are the same, but the next two terms have a minus sign instead of a plus sign. So we're going to have minus 29 times 0.866 minus 19 times minus 0.5. And when you've done all these calculations, you get minus 1.4 MPAs. Just numbers. And then you get tau x1, y1 equal to, it doesn't have the average, and it has minus on the second term and plus on the third term, and it has sine instead of cosine. So it has minus 29 and multiplies minus 0.5 plus minus 19 that multiplies 0.866. And when you plug all this stuff in, you get 29 and 0.5, you get minus 31 MPAs. All right, so this is boring, but it's not that challenging, right? It's just substitute your numbers in, no problem, you get your numbers out, and so you have now the stress state on this angle. So one thing I want you to note, so note that if I do sigma x plus sigma y over 2, which is minus 17 MPa, sigma x plus sigma y over 2, which is minus 19 MPAs, is also equal to sigma x1 plus sigma y1 over 2. If you sum this and you divide it by 2, you also get minus 19. And of course, this is true, because if you look at this equation, when you sum these two and divide by 2, you just get the first term, right? OK, so the other thing that we are asked to do is to draw the stress state on the element rotated. So we can draw this. So I can erase this, right? OK, so we can put it side by side so that we can see what they look like. So if we put it side by side, now we have the element that's rotated by 15 degrees, so this looks like that. And it's still an element that is a point P. So on this element, we see that sigma x1, remember this is the x1 phase now, sigma x1 is minus 32.6, so again it's compressive, 32.6 MPa. Sigma y1 now has become compressive, 1.4 MPa. And then the shear stress is still negative, so it still goes against convention like that. And the magnitude is 31 MPa. So you were told, and if I want to write it in component, sigma at this point, but in the prime axis now is minus 32.6, minus 31, minus 31, minus 1.4. Of course, all in MPAs. OK. Yeah?
When I added them up, they don't kind of add up to 19 when you take the average? I think 32.6 and 1.4.
Divided by 2, remember.
17.
You have to divide by 2? Yeah, did I screw up the numbers? 32.6, 1.4. I got 32, 33, 34 divided by 2 is 17. Why not?
17 too. It's so under your note.
Oh, is the other one 17?
It's supposed to be 17. You wrote 19.
Oh,
It should be
okay.
17.
Yeah, you wrote 19, it should be 17.
Oh, yeah, okay, it's fine.
But they're both 17.
Yeah, they're both 17.
In the equations you put 17, but there you put 19.
17 is the average.
Yeah,
OK. Do I have it wrong?
you wrote that the average is 19 right there.
Oh, sorry about that. I'm sorry. I'm totally blind. I'm trying to understand what the problem is. Yes, sorry about that. We good? Didn't mean to mess you up. OK. I got messed up between the shear stress and the average. OK?
I have a question about the
Yes.
convention of positive shear stress. Could you explain what the convention is?
The convention is right here. Tensile stresses are positive in tension. Shear stresses on an x face, it goes with the y-axis. On the y face, it goes with the x-axis. Right? And of course, they must be equal in magnitude so that the element does not spin around. Okay? Are we good? Any other mess up in algebra? Okay. So now, I mean, this is just plug in the numbers and find what you're asked to. But there is a little more deeper meaning to all this. So first of all, let me ask you something. So what is the stress at point P, right? Because we have a stress which is this guy according to the first calculations, I mean what we're given, and now we find a totally different state of stress at the same point. So what is this story? Does the stress change depending on which way you look at it? Right? Stress should be stress. Should not be something that I measure as something and somebody else measures as something else. Because say, for instance, that I want to decide, will the material fail at this point P? Well, if I look at the component, maybe what I think is going to be different from what somebody else thinks, because we see different numbers. Right? So in order to understand what is really the state of stress at that point and will the material fail at the point, we need some kind of measurement of the stress, which does not depend on which way your head is turned. Right? We need something which is an understanding of stress, which is a little more deep than this kind of simple turn the axis, turn the crank, find x1, find y1. We want to know what all this means. So the answer, really, the basic answer is, so what is the stress at P? Is it this? Is it that? As many axes I rotate, I'm going to get different sets of numbers. And how big is the stress? How do I decide how big is the stress? So we want to understand a little more about these whole concepts, these whole ideas. So what we're going to do is we're going to go back to very basic concepts that you're more familiar with. Because stress is a little more, it's a new concept for you guys. So let's start with something that you already know, right? So let's say that so we start with something that you've seen before and you know how to deal with. So instead of dealing with stress, let's just deal with a vector. Let's deal first with vector quantities, okay? So let's say that I am sitting here, and I make my own reference frame with my arms. This is my y-axis, this is my x-axis. And there is rain coming down. There is wind, there is rain coming down, and the rain comes down, not straight down, but at a certain angle, right? So I'm sitting here. That's me, and make an eye. And I'm sitting happy, and I put my arms. Where's my thumb? That way. And I make my axis, x and y. And the rain is coming down at an angle from the horizontal. So this is my rain coming down. And this is the velocity of the rain, v rain. I look at the velocity of the rain, and in my xy coordinate frame, I see that the horizontal velocity is 4 meters per second, and the vertical velocity is -3 meters per second. That is what I say is the rain, right? Velocity of the rain. Then over here, there is my husband. Always sees things different. So that's him, sitting there. He looks down, and he puts his arm like that, right? Always contrary. Puts like that. That's x1. And he says, this is y1. And he's under the same rain, exactly the same rain. And he sees the rain, and he says, as always, you're totally off, right? Because as far as I can tell, this rain has a horizontal velocity of 3 meters per second and a vertical velocity of -4 meters per second. That's what he sees, right? So here we are. with just a simple thing as the velocity of the rain, but we have two ways of looking at the velocity of the rain. I see these guys, so this is going to be Vx and Vy, and he sees this guy, this is going to be Vx1 and Vy1, right? But rain is a physical quantity. There is only one velocity of the rain. So there must be something on which we must agree, right? So there is something more to the whole story of what different people sees. So the V is a physical quantity. So when we describe the rain, there must be a way for us to describe it in ways in which we all agree about the rain, okay? So based on this simple picture here, we're going to make three notes that are going to help us to deal with the whole mess of stress, okay? So the first note that I want you to see is that the way that we transform the components of velocity is always the same. So say you know how to, so if I give you Vx and Vy, I'm sure you have done millions of problems in physics in which you're asked to find velocity in a different coordinate system, right? You take Vx and Vy, you project them on the x1 axis, you project it on the v1 axis. So once somebody tells you Vx and Vy, you've done a number of these things in which you get Vx1 is equal to Vx, and I didn't tell you, but this angle here is our good old angle theta. So Vx1 is Vx cosine theta plus Vy sine theta, actually minus, no, plus, Vy sine theta. And Vy1 is equal to minus Vx sine theta plus Vy cosine theta, right? You have derived these equations a gazillion times. So one thing that is very important to notice is that once you derive these equations, if instead now of being a velocity, I have a force, right? Different kind of vector, but still a vector with the fx and fy. And I want to know now if somebody, is applying a force in the xy frame with certain components, and I want the components of the force in a different frame. These equations here, the equations are general. These equations are general, and they apply to any 2D vectors, right? You can write them in matrix form if you want, Vx1 with a matrix that's called the rotation matrix. But even if you just write them as equation, this equation, whatever is the vector, the meaning of the vector, velocity, force, whatever vector in 2D, you can always rotate the components with the same equation. So that's the first thing that we want to note about this whole little sideway trip into vectors. Another thing that we can notice is that, actually here, let's skip it. Another thing that we can notice, so that's note number one. Note number two is that there are some special orientations and some special values of components, right? So if this is the rain, and the rain is going that way, just as it's drawn, right? I can start rotating the axis in different axes, and whatever axis I have, this equation here is going to tell me the components. What if as I rotate the axis, I go one of the axes exactly parallel to the velocity of the rain, right? That's one of my possible orientations. If I do that and I put my axis exactly parallel to the velocity of the rain, so this is one axis now, and this is another axis, I find that my components of velocity now are Vx1 is going to be the magnitude of the rain, 5 meters per second, right? And the y is going to be 0. So there is going to be, of all this angle theta, there is going to be a special orientation. So there is a special orientation. There is a special axis orientation where one component is max and one component is 0. So if I choose, if this is my velocity and it looks like that, if I choose this axis here and I call them axis 1 and axis 2 without x or y, just axis 1 and axis 2. In this axis here, I have v1 equal to 5 and v2 equal to 0. These are called the principal axes. So these are called the principal axis for this vector. Principal axis 1, 2. Axis. And the value of these components in this principal axis are the principal values of the vector v. Okay? So there is an orientation in which I get x and y component, which are, the x is as big as it gets. There is no possible component bigger than that. You know, because that's the same as the whole velocity, 5. No matter where you orient things, you're never going to find in any axis a component of velocity bigger than 5. Are we good? So there is a special axis where I get the maximum magnitude of the component for one of the two components, and I get 0 for the other component. These axes are called principal axes, and the value of the components in those axes are called the principal values. Okay? So this is, so I'm giving you 3 little nuggets of knowledge on vectors that we're going to reuse for stress. Okay? So bear with me with one more nugget of knowledge. There is one more nugget of knowledge that is, there are things called invariants. Okay? So there are quantities called the invariant. Invariants means they do not vary. There are things that are called invariants, which are things that me and my husband can calculate and agree on, right? Right now we are at odds because we are saying, I say, oh, Vx is 4, Vy is minus 3. He says, no, Vx is 3, Vy is minus 4. But there are something that we can do with this knowledge that we have. I have only this knowledge. He only has this knowledge. And that's really the extent of his knowledge. That if we use it, we can calculate something on which we both agree. So what is something on which we both agree for this kind of vector? The magnitude, right? So for a vector, we can calculate the magnitude and agree on it. So for a vector, I can take my Vx square, my Vy square, and take a square root, and he can take Vx1 square plus Vy1 square and make a square root. And we calculate it independently, and we both get 5 meters per second. So invariants are the same in all coordinates. So even if you come there, and you orient yourself like upside down, hanging from the ceiling, and you measure your velocity, when you calculate Vx and Vy and you do the magnitude, you're going to find exactly the same magnitude, right? So why are we doing all this? We're doing all this because we want to understand something similar about the stress, okay? So the same way as for velocity, there are something in which we agree on like the magnitude of the velocity, and we can talk to each other and say, how big is the velocity? 5, 5, 5, everybody agrees. We want something like that for stress. We do not want something that, you know, Jim finds a certain set of number, Ann finds another set of number, and we cannot say how big is the stress, right? So we want to find something like that that works for stress. And the reason that we can do this is because stress is not just a random collection of numbers. It's not the same as, you know, we write it as a matrix. But these things that we put in the matrix, they're not just a random collection of numbers. These things are the Cartesian components of the stress at point P. This is not the same as filling up a matrix with, you know, Jim, age, religious preference, goes to the gym 3 times a week, and, you know, and it's not like a matrix of random number that do not connect to each other. The components of stress that you put in this matrix are the Cartesian component of the stress, the same way as the velocity, are the Vx and Vy are the Cartesian component of a velocity. Stress is a physical quantity. It exists at a point. It exists independent from whatever coordinate system you use. The rain is there. It rains. You get wet. It comes down at a certain speed. It exists in itself independent if you have a coordinate system x or y, right? If you load the body with forces and whatever, the stress at this point exists as an entity independent of what axis you have. The stress is called a tensor. Tensor, right? So, same way as this is a vector, stress is a tensor. Actually, if we want to be extra fancy, like in graduate school, you can put a little squiggle underneath to show that this is a tensor, right? And so this is actually the stress tensor. Stress tensor. And these happen to be the Cartesian component of the stress tensor in the xy reference frame, the same way as these guys were the Cartesian component of V in this reference frame. And the same way as when you rotate the frame, you're going to have different components for velocity. When you rotate the frame, you're going to have different components for the tensor. Now do you understand what we were doing? Right? We were finding the Cartesian component of the stress in different reference frames. So this equation here, these equations here, are not just a bunch of random equations that mean nothing. These are exactly the corresponding equation to that. Those are equations that tells you if I know the component of stress in that reference frame, I find the component of stress in any other reference frame that happens to be rotated by an angle theta with respect to the original by plugging the numbers in here, the same as you plugged in there. See how cool it is? Isn't that like overwhelmingly awesome? Yeah. That's the spirit. So now, this whole thing, now the other cool thing though is that, you know, like this thing applies, when we derived this one, you didn't derive it, but if you had done the work of deriving this, to derive this, we would have used all this concept of equilibrium and balance the wedge and all that, right? To make up these equations. But once we have derived it for once we have derived it for one tensor, stress, this equation apply to any 2D, because we are doing only plane strain now, remember, plane stress, We apply to any 2D tensor, any 2D tensors. So if I have the strain at a point, right? So for instance, if I have the strain at a point, epsilon xx, epsilon xy, epsilon xy, epsilon yy, and I want the same strain in a rotated frame, so I want epsilon x1, x1, epsilon x1, y1, epsilon x1, y1, epsilon y1, y1. If I want this one, the strain in a rotated frame, I don't need to redo a mess of geometry and stuff like that. I'm done. Lazy as can be. I've done it once. I've done it forever. Okay, so these transformations apply to any tensor. For example, strain. Why? Because strain is a tensor. So the strain tensor, strain is a tensor as well. For instance, let me show you a little, actually, let me do it here. And this is a little bit of an aside. We're not going to go there today because I want to do a little bit more about stress before we go. But for instance, if I take a bar like this and I draw a square on it, and then I stretch it so that the bar looks like that, you say, oh, it's easy. If this is x and this is y, then I can see that my strain is going to be positive in, going to have a positive epsilon yy and negative epsilon xx. Is there any shear here? Gamma xy, 0, right? But then I can come to you and say, well, look at that. I draw a little square inside, like that. And if I look at what happens to this square, look at that. Whoa. Right? It's sheared. And now I know that I can calculate this. If I tell you what is epsilon xx and epsilon yy in this frame, if I rotate by 45 degrees and I want to find what is the strain which is going to have shears in that reference frame, I just take away the sigma, I put in epsilon, and I'm done. Right? So understanding what we're doing is really important because it makes it so that what we do extends and applies to other quantities. If you have other tensors, you guys are material scientists. You're going to have tensor up the wazoo. You're going to have, the tensor that describe the crystallographic orientations, all kind of complicated things. But you're not going to have to do any more of this work because you have done it. And you're lazy. You don't want to redo it. You're just lazy as much as I am. OK, so let me see. I have 5 minutes, so I'm going to tell you one more thing, which is really another. So we're doing all this because we are going to get into this way to look at these equations so that it kind of makes sense. Right now, it's a soup, right? Like you look at this and you're like, how can I interpret this? I mean, I cannot see these equations. You do not have a mind that processes how then the stress changes with x and y. Remember what I told you? We are interested in a bunch of things for the stress. We would like to figure out, are there things for stress such as principal axes, which are axes where these components take their maximum values? We are interested in that because if there is like a set of axes where we have a maximum tensile stress, that's the axis in which we have to be worried and look for cracks in that orientation, right? So, and we want to know if I talk to another person, even my husband, and we look at a certain state of stress, are there any quantifications of the stress that we can agree on? Are there any invariants for stress? You already find an invariant for stress, by the way. What is the first invariant for stress that you found out? The average. Because we already said that sigma x1 plus sigma y1 divided by 2 is equal to sigma x plus sigma y divided by 2. So actually, pretty nice. We already have the first invariant that we found. So we found already an invariant. for stress. We found that sigma x plus sigma y over 2 is an invariant. An invariant means people in different frames look at the stress, they measure it, they find the same number. But we want a little more than that. So, because these equations are so ugly, some guy called Moore came up with a cool way to massage this equation into something that can be understood. Okay? So he kind of went there and he said, really, I mean, if I look at these equations, these describe how, if I look at all these faces, as I rotate my little element, as I rotate it, how the stresses on the face change. Right? So let's say that we look at the y1 face. This is what it looks when it's not rotated, and then if I rotate it, it's going to be different. And by the way, to understand this, we do not need to look both at the y prime phase and the x prime phase, because one is the other one just by 90 degrees, right? So we don't need to actually, we can even forget the first equation. We can just say, if I look just at the y phase, and I imagine that I start straight up, and then I rotate, and for each rotation I have different stresses. How do I quantify these two guys? How do I understand what those means? So this Moore guy came up with a cool idea. He said, okay, so I want to combine these two equations so that I get something that I can work with. So bear with me right now. So the first thing that you do is you take sigma y1 and you subtract the average stress. The average stress is sigma x plus sigma y over 2. Let's call this sigma bar, the average. I take sigma 1 and I subtract the average stress. So I get minus sigma x minus sigma y over 2 cosine of 2 theta minus tau xy sine of 2 theta. That's just what this is, right? I say, that doesn't look any better than what I had before. Then the minus is on the fraction, all of that. Then I say, okay, then what I'm going to do, just because this is not ugly enough, I'm going to square it. Okay, I can square it. You say, whatever, square it. Then I say, no, you're not done yet. I also want you to subtract tau x1 y1 squared to the whole mess. So you have to say, my gosh, yes, okay. Sigma x minus sigma y over 2, and that is a sine of 2 theta, and then plus tau xy cosine of 2 theta. All right, I can do that. I square it. Why do you want me to do all this? You're like, what is she doing on this stuff? I tell you what am I doing. If I do this, and I calculate the square, this one gives me this square as a cosine square. Sine square, I sum it makes 1. I do the same thing, sine square plus cosine square, I sum it makes 1. The mixed term, this is minus minus, and this is plus minus. They are the same but with opposite values. So the mixed term, boom, fall out. So after I've done all that, on the right-hand side I find sigma x minus sigma y over 2 squared plus tau xy squared. That's what I find. And you say, but so what? Well, you say, what, so what? Because you're forgetting that this is sigma y1 of theta minus sigma bar square minus, you say minus? Should be plus. Sorry. Plus tau x1 y1 of theta squared. You say, so what? Because you didn't think of this part. You didn't think that on this side I have a function of theta. And on this side I have something which is not a function of theta. It's a constant. Okay? it's a constant that doesn't change with theta. So it says for any orientation theta, if I combine this thing in this way, I get a number that depends on whatever stress I had to start with. Okay? So let me show you one more thing and then we go. Because I want you to look at this equation and tell me how does this compare to this equation. So, if I call this x and I call this y, and this is just a number, this equation here tells me for all values of x and y that satisfy this equation, this means that every value of x and y that satisfies this equation sits on what? A circle. A circle of radius r that has the center at xc 0. So this describes a circle. It's called the Mohr circle of stress. You're going to hate it on Wednesday. We're going to do a lot to understand more what does this mean in terms of describing the state of stress at a point. Right now it seems like a soup. But I hope that by the end of Wednesday, you're going to say, I love the Mohr circle of strain, because it makes you understand what these equations are. I know you're not going to love it. I just hope you're going to love it. But we're going to start from here on Wednesday. We're going to see where we're going, okay? Bye. Now you know why Lorna is in London.